Next time you're on a plane, look down at the bottom of your window. Right there, at the very edge of the glass, or what you think is glass, there's a tiny hole. Maybe you've noticed it before and assumed it was a manufacturing defect. Maybe you've seen frost form around it on a cold day and thought something was leaking. Maybe you've even thought about complaining to a flight attendant that your window is broken. Here's the twist. That hole isn't a flaw. It's not damage. It's not an accident. That tiny hole is one of the most quietly brilliant pieces of engineering on the entire aircraft. And it exists because of a string of disasters in the 1950s that investigators spent years trying to understand, involving planes that were literally falling out of the sky for reasons nobody could explain. By the end of this video, you're going to understand exactly why that hole is there, why every single passenger window on every commercial jet on Earth has one, what would actually happen if it wasn't there, and why the shape of the window itself, that smooth, rounded rectangle you've never thought twice about, was paid for in human lives before engineers got it right. Let's start with something most passengers never think about. Your airplane window isn't actually glass. It's acrylic, a tough, lightweight plastic, and it's not a single sheet. It's 3 separate layers stacked together, each one with a completely different job. The layer closest to you, the one you can touch, lean your head against, and smudge with your fingerprints is called the scratch pane. Its job is almost embarrassingly simple. Protect the layers behind it from passengers, from bags bumping into it, fingers pressing on it, kids drawing on the fog with their fingers. It is not structural. It is not holding anything back. Think of it like a phone screen protector. It's there to take the abuse so the important stuff underneath doesn't have to. Behind that scratch pane is an air gap, and then the middle pane. And this is the one with the hole in it, the one this entire video is about. We'll come back to exactly what it does in a moment. And, finally, the outermost layer, sealed directly against the sky, is the structural pane, the real workhorse of the entire window assembly. This is the layer engineered to survive the brutal pressure difference between the cabin you're sitting in and the thin, freezing air thousands of feet outside. 3 layers, 3 jobs. And understanding why airplane builders settled on this exact 3-layer system, with a hole drilled through the middle one, requires going back to a pressure problem that engineers in the early days of jet aviation did not fully understand, until people died finding out the hard way. Before we get to the hole itself, you need to understand the actual problem it's solving, and that starts with altitude. A commercial jet cruises somewhere around 35 to 40,000 feet. At that altitude, the air outside is so thin, so low in oxygen and pressure, that an unprotected human would lose consciousness within minutes. This isn't a minor inconvenience. It's genuinely lethal territory. Mount Everest's summit, for comparison, sits at just over 29,000 feet. Cruising altitude is higher than that. So here's the engineering challenge airlines face every single flight. How do you keep several hundred people alive, comfortable and conscious inside a metal tube, flying through air that would kill them in minutes if they were exposed to it directly? The answer is cabin pressurization. Aircraft systems pump and maintain air inside the cabin at a pressure roughly equivalent to what you'd experience at 6,000 to 8,000 feet above sea level, similar to a high-altitude city like Denver or parts of the Rockies. Not sea-level pressure, but comfortable and safe enough for nearly everyone to breathe normally without supplemental oxygen. Here's the catch, though. To hold that internal pressure steady while the outside air pressure is dramatically lower, the aircraft's entire structure, including every window, has to act like a sealed pressure vessel, constantly pushing back against the urge of that higher pressure cabin air to escape outward into the thin air outside. That pressure differential isn't trivial. It's a genuine, continuous structural force acting on the fuselage and every window cutout in it, for the entire duration of every single flight, on every single aircraft, multiple times a day, for decades of service life. And it turns out that this exact stress, applied over and over, takeoff after takeoff, landing after landing, is precisely what caused one of the most infamous chapters in aviation history. In the early 1950s, the de Havilland Comet was the future of aviation. It was the world's first commercial jet airliner. Sleek, fast, revolutionary, flying higher and faster than anything passengers had experienced before. Airlines were thrilled. The public was thrilled. This was the jet age arriving ahead of schedule. And then, within a few years, comets started falling out of the sky. Multiple Comet aircraft suffered catastrophic in-flight breakups. The fuselage simply failing, mid-flight, at cruising altitude, with no warning. Investigators were baffled. These were well-built aircraft, flown by experienced crews, maintained properly. There was no obvious single cause. The investigation that followed became one of the most important in aviation safety history. Engineers eventually traced the failures back to something almost shockingly small: the corners of the comet's windows. They were square, sharp right angles, the way you might design a window if you were thinking purely about aesthetics or simplicity, with no idea what repeated pressurization cycles would do to that exact shape over time. Here's what was happening. Every single flight, as the cabin pressurized on takeoff and depressurized on landing, the fuselage flexed, expanded slightly, then contracted. At the sharp corners of those square windows, that repeated stress concentrated into a single point far more intensely than anywhere else on the aircraft skin. Engineers call this metal fatigue, microscopic cracks that don't show up after 1 flight or 10 flights or 100, but that grow, invisibly, cycle after cycle until one day, without warning, the metal simply gives way mid-air, at full cruising pressure, all at once. The comet disasters fundamentally changed how every aircraft on Earth has been designed ever since. Square corners on pressurized cabin windows were eliminated industry-wide. Every passenger window you've ever flown next to, that smooth, rounded, almost oval shape, exists specifically because square corners under repeated pressure cycling can fail catastrophically. That rounded shape isn't a stylistic choice. It's a direct, permanent engineering response to a tragedy that cost real lives before anyone fully understood why it was happening. But solving the corner stress problem with rounded shapes was only half the fix. Engineers still needed a way to manage the raw pressure differential itself, every single flight, on every single window, without putting all that stress permanently on one fragile layer of acrylic. That's where our tiny hole finally enters the story. Now we're ready for the actual mechanism, the thing you came here for. Remember the 3-layer window: scratch pane, middle pane with the hole, and outer structural pane. The hole, called a bleed hole or breather hole, is drilled through that middle pane, and its entire job is to manage exactly where the pressure difference between cabin and sky actually gets applied. Here's the key insight, and it's almost counterintuitive. Both the middle pane and the outer pane are individually strong enough to handle the full cabin-to-outside pressure difference completely on their own. Either one alone could theoretically do the job, but engineers didn't want both panes sharing that stress equally, all the time, for every flight, for the aircraft's entire operational life. Instead, the bleed hole lets the air pressure in the gap behind the middle pane equalize with cabin pressure, which means, under completely normal operating conditions, only the outer pane actually bears the brunt of the pressure differential. The middle pane just sits there quietly, unstressed, doing essentially nothing, held in reserve. As Marlo Monker, Director of Technology at GKN Aerospace, a major aircraft window manufacturer, explained it directly. The bleed hole exists to let pressure equilibrate between the cabin and the gap behind the middle pane, specifically so that cabin pressure during flight only acts on the outer pane. So why deliberately design it this way, with one pane absorbing all the stress while the other does nothing? Because this creates a genuine failsafe. In the extraordinarily rare event that the outer pane is somehow damaged or fails, a bird strike, debris impact, an undetected manufacturing flaw, the middle pane is sitting right there, completely unstressed, fully capable of instantly taking over the entire structural load and containing the cabin pressure on its own, keeping everyone inside safe while the aircraft descends to a lower altitude. It's a built-in backup that's been silently doing nothing on every flight you've ever taken, just in case the day comes when it's needed. There's a second function the bleed hole performs, too, and it's one you've probably actually witnessed without realizing it. Fighting condensation. As an aircraft climbs and the temperature outside plummets to far below freezing, moisture in that sealed air gap between panes would otherwise condense and freeze, fogging up your window from the inside. Exactly the kind of frost ring you may have noticed forming right around the hole itself on a cold flight. By letting that trapped air continuously exchange with the relatively warmer, drier cabin air, the bleed hole keeps the gap from accumulating moisture, keeping your window clear enough to actually enjoy that view you paid extra for. And there's a third, more subtle benefit worth understanding: gradual pressure loading. One consulting engineer explained it with a simple analogy. There's far less impact on an object if you gently lay a hammer down on it versus dropping it from a height. The bleed hole works the same way for the outer pane. Instead of the pressure differential slamming onto that outer layer instantly and abruptly every single takeoff, the bleed hole lets that load build up gradually as the aircraft climbs, smoothing out the stress curve over the entire ascent rather than hitting the structure all at once. Over thousands of flight cycles across an aircraft's decades of service life, that gradual loading meaningfully reduces fatigue. The exact same kind of fatigue that doomed the Comet, just managed correctly this time. So, in 3 sentences, the hole protects the structural integrity of your window by directing stress to the pane best designed to handle it. It prevents fogging and frost by managing moisture in the air gap, and it smooths out the physical loading of pressure during climb and descent, reducing long-term fatigue. One tiny, almost invisible hole, quietly doing 3 different safety-critical jobs on every flight for the entire lifespan of the aircraft. This raises an obvious question: what would actually happen if that hole got blocked? In practice, modern aircraft windows are engineered with enough redundancy that a single blocked bleed hole wouldn't immediately cause a structural emergency. The outer pane is still rated to handle the full pressure differential on its own if needed, but blocking it would defeat the entire point of the fail-safe system. You'd lose the pressure equalization that protects the middle pane from unnecessary stress, you'd likely get fogging and frost buildup with nowhere for that moisture to go, and over time, repeated full-pressure loading without that gradual bleed-off could accelerate fatigue in ways the original design specifically intended to avoid. It's not catastrophic in the short term, but it quietly undermines decades of careful engineering built into that window for a reason. This is also a good moment to debunk a myth you may have heard, that the hole exists to let a little fresh air in for ventilation, or that it's somehow connected to the cabin's main air circulation system. It isn't. Cabin air circulation and filtration happens through a completely separate system entirely. Large-scale air handling units that exchange and filter cabin air dozens of times per hour. The bleed hole has nothing to do with the air you're breathing. Its entire purpose is structural and moisture management, confined entirely to that narrow gap between 2 panes of acrylic, doing a job most passengers will go their entire lives without understanding. It's also worth addressing why airlines ask you to keep your window shade up during takeoff and landing. A completely different design feature, but one people often mentally lump in with weird window rules. That's not related to the bleed hole at all. It's about allowing your eyes to adjust to outside light levels in case of an emergency evacuation during the highest risk phases of flight, so you're not suddenly blinded stepping from a dim cabin into bright daylight, or vice versa. Different window-related safety feature, different reason entirely, but it's a good example of just how much invisible engineering and procedure surround something as simple as the window you're sitting next to. Here's what makes the bleed hole such a perfect example of something much bigger about how aviation safety actually works. Almost none of it was figured out in advance, purely through theory. Most of the safety features you don't think twice about. Rounded windows, the bleed hole, redundant structural panes, even cabin pressurization limits themselves, exist because something failed first. People sometimes died, and engineers traced the failure back to its root cause with forensic precision, then built a permanent fix into every aircraft built afterward. The comet disasters alone reshaped how every pressurized aircraft window on Earth has been designed for the past 70 years. That's not an exaggeration. It's the literal engineering lineage of the window you'll sit next to on your next flight. Aviation safety, in a very real sense, is written in the lessons of past failures, encoded permanently into design standards so that the same mistake never has to happen twice. And that's really what makes the tiny bleed hole worth understanding. It looks like nothing, an easily overlooked pinprick you might mistake for damage, but it represents a direct, traceable line from a 1950s tragedy to a quiet, elegant piece of redundant engineering that's been keeping you safe on every flight since, without you ever needing to know it was there. So, next time you're cruising at 35,000 feet, glance down at that tiny hole near the bottom of your window. It's not a flaw. It's not a defect. It's not something to worry about. It's a fail-safe pressure valve, a built-in anti-fog system, and a fatigue-reducing engineering trick. 3 jobs, quietly handled by one hole, on every commercial jet on the planet, because decades ago, people lost their lives discovering exactly what happens when pressurized aircraft windows aren't designed correctly. That hole is, in a strange way, one of the most reassuring things on the entire aircraft. It means someone already thought about the failure you'll never experience. If pulling back the curtain on the invisible engineering hiding in plain sight is your kind of video, you're going to want to stick around, because the world is full of these tiny, overlooked details with massive stories behind them. Drop a comment with the next everyday travel mystery you want explained, hit subscribe, and I'll see you in the next one. This is the SRI of the airplane window bleed hole. Let's get into it.